So you can see a bunch of people from our side at ZSW, but also we took the chance to collaborate with Axel Gross' team and Manuel Dillon, for instance. With the Kaiser group, with Sonia Zoke for the operando X-ray diffraction I will show later, with the Christian for the TM measurements, and we had also a guest scientist coming from Riga, Latvia, Gint, who joined us last year, and he was with us for about 10 months, and he was funded by the European Commission. So you see a little bit of different expertise. Yeah, I think this is one of the strengths of Polis. Yeah, so we could really get what we wanted to have and try to explain things to having a deeper understanding of things. The title of the first slide, I actually stole it from the conference that ZSW and HIU organized last year on sodium-ion batteries. So an emerging technology on the way to market. Yeah. I think that the biggest breakthrough or the biggest push was when last year CATL announced that they were going into production of sodium-ion batteries. Yeah. But besides CATL, there are many other companies working on sodium-ion batteries. This doesn't mean that our job is actually done. If you compare to what happened to lithium-ion batteries, the first one was commercialized in 1991 by Sony. Relatively poor specific energy, so about a 90 watt-hour per kilogram. And now, after 30 years, yeah, we are actually almost hitting the 300 watt-hour per kilogram on the best, most performance cells. When we try to compare sodium-ion batteries and lithium-ion batteries, what is actually the pros? What are the cons? Definitely, the two technology will be side by side. The lithium-ion will be, or at least for now, is the most performant one. Of course, much more years of research and development in that field. But one pro of the sodium-ion technology is that it has a similar rocking chair principle as lithium-ion batteries. So this also makes the technology drop-in kind. So we have actually low capex. We can, as we also heard before from Julian, we can pretty much use the same coating technology. Of course, we have to adjust some parameters, turn some knobs, but in principle, the two technologies are very similar in terms of processing and making of the battery cell. What the sodium-ion actually have in their pocket, let's say, is that they are supposed to have high power, less sensitive to operating condition. We all know that this is a big issue for lithium-ion batteries. Going to particularly low temperature will lead to lithium deposition, then dry growth, and then safety issue. If you go to higher temperature, well, you start degrading the cathode material. So probably sodium-ion batteries have an edge in that respect, in that KPI. And also safety. One of the good thing about sodium-ion batteries in respect to safety is that actually they can be completely discharged, and shipped. This doesn't work with graphite. You always have to have about 30%. This is what they recommend, and then you can ship the cell. Otherwise, you will have problems with SEI destabilization, let's call like that. But apparently, you can ship a sodium-ion cell even if it's a 0 volt. And this has direct impact on the safety, because basically you have a completely uncharged cell. On the con side, well, We have higher average potential of the hard carbon as compared to graphite. This basically impacts directly the capacity of the cell. Well, not the capacity, sorry, but the energy of the cell. So at least at the moment, we see that sodium-ion cells have lower energy for both volume and weight as compared to lithium-ion batteries. And of course, still lower charge-discharge life cycle as compared again to lithium-ion batteries. Now, as I said, the two technology will most probably work side by side, depending on the application. For now, sodium-ion batteries are meant to go or to be used for light-duty vehicles, stationary application, and then of course more depends on how far we go in terms of material development, electrode development, cell development, and how much energy we can actually store in the cell, in the battery pack. So why layered transition metal oxides? Of course, if we look at the landscape of cathode material for sodium-ion batteries, we can group the materials in three large families. So the Prussian blue analogs, the polyanionic materials, and the layered transition metal oxides. Then again, the transition metal oxide, layered oxides, they have an edge in respect to the other probably because they actually share similar production processes as and processability of lithium-ion batteries cathode active material. Let's just think all the cobalt oxide, nickel, manganese, cobalt oxide, so all the layered oxides. Can be made with a high tap density. Tap density will directly impact the energy density that you are actually able to pack in your cell. And they can be tuned in respect to capacity and working potential depending on the selection of the transition metal. Now, we have basically two key parameters to increase the specific energy at the material level. We can work with, so we can work aiming at having higher specific capacity, or we can actually aim at having higher working potential. One thing doesn't exclude the other one. Sorry, wrong button. So we tried to come up with this table, and what we want to be, or what we want to do, is basically to go in this direction. So increase the average potential of the cathode material and increase the reversible specific capacity of the cathode. This is where our material is positioned. Is basically a sodium deficient manganese nickel layered oxide, manganese 3/4, nickel 1/4. I think most of you are actually familiar with the Delma notation. Yeah? Sorry, I realized that actually my PowerPoint didn't like to have the O at the beginning. So this would be an O3 type structure. This would be an O2 type structure. And in the both case, basically, we have the sodium sitting on the octahedral sides. The difference is that basically on the O3, we have 3 MO2 layers that are needed to describe the unit cell, and the O2 is where we need only 2 of them. Same thing would be for the P3 type structure and for the P2 type structure. What actually is different is that in this case, the sodium will be sitting at the prismatic site. So there was actually a very nice publication recently this year done by Maider, Dominic, and Stefano, where they actually come up with a very nice review and a little bit trying to help research in designing layered oxides. And basically what they have been doing was to not only looking, let's say, at the abundancy price and well, the price, of course, in dollars per kilogram, yeah, but also the variation of the price with time, and they introduced this term called the specific transferred electrons, STE. Now, if you look at this plot, basically, you can see that nickel still gives an edge in terms of performance. So you have higher average potential, yeah, and so eventually, although we would like to reduce the nickel content for some kind of application where we need more performance, yeah, a little bit of nickel might be still beneficial. Of course, we are not considering cobalt at all in this case, but nickel, it's still a little bit there. So the P2 kind of material that we have, well, if we basically look at the very upper left graph, what you can see, this is actually a galvanostatic profile. You can see that when you start your oxidation, you have basically a slopey profile, and this is a sorry, this is actually the nickel 2 plus oxidation, and then at one point you get into a plateau at about 4.2 volt, and this is where you have a phase transition, so from P2 to O2, right? It's expected that there you have nickel 3 to nickel 4 plus oxidation. You might have some oxygen redox reaction, eventually some oxygen evolution. What are actually the problems of P2 layered oxides? Well, there is one problem that actually has to go with the bulk degradation, and this is exactly what I just said. So the phase transition from P2 to O2. This leads to relatively high volume change and eventually cracking. Yeah? And another path actually follows the surface degradation, where we actually have side reaction, eventually transition metal oxide, transition metal dissolution, oxygen release, and the creation of a new insulating surface layer. So when we started working on the sodium manganese 3/4 nickel 1/4 oxide, we looked into a synthesis that could have been scaled up. Okay, so of course we went into co-precipitation using two of the transition metal precursors in form of nitride. Of course, we put everything in a flask, stirring, and then we get the first hydroxide precursor, which is then followed by a solid state synthesis, so treatment, impregnation with the sodium hydroxide, and then heat treatment at 900 degrees C for 12 hours. And this is what we get: spherical particles in the range of 20 to 30 nanometers. Yeah? And what we have also looked was how actually the temperature would influence the structure of the material that we have, as well as the sodium content in the structure. So what we observed was that at low temperature, so below 700 degrees, the P3 structure is formed, and this is independent from the amount of sodium that we put in the structure. When we go to 700 today, 800, then we have a mixture of P3 and P2 at low sodium content. When we go into higher solid content, sodium content, then it's going to be a P2 to O3. And of course, when we go then above 825 degrees C, we only have a P2 structure. And this is what we actually selected for further investigation. Now, going back to the degradation mechanism of the layered oxides, yeah, we might come up with different strategy to mitigate the capacity fading. There has been several reports in literature for doping, but also for coating. Now, with the doping, what we are trying to do is actually to stabilize the bulk, yeah? So to prevent the P2 to O2 phase transition. With the surface coating, what we are trying to do is to prevent any side reaction happening at the surface. Yeah? So we actually followed both approach, and this is what is my talk about today. So to synthesize the magnesium-doped sodium manganese nickel oxide, please note that actually the level of doping is relatively low. We looked first in the literature, and this was a publication we saw, and this is actually from Teófilo Rojo and Peter Bruce, published a few years earlier, where they already investigated the influence of the magnesium doping in a very similar structure. Of course, then the synthesis was all solid state, so the particle morphology couldn't be controlled as good as we can actually do. Why I'm saying as good? Well, we have seen before from Julian, most of the, if you are let's say, familiar with coating technologies for lithium-ion batteries and material for lithium-ion batteries, you will see that most of the materials actually have a spherical particle architecture, yeah? So with the small crystallites, but then aggregates and secondary particles that are in the micrometer range. This actually is or gives you an edge in terms of handling of the material when you think about producing gigawatt hours, yeah, of cells, but this is also what we can do in our pilot lines, where we manage 100 kilo of materials per batch. Yeah? So you don't want to have actually very small particles flying around. This is one thing. Usually, spherical particles, they have better flow ability. They pack more density, so you get more tap density, and so on. So we started actually, as I mentioned, with the baseline material, 75-25. This is the ratio of nickel and manganese. And then we had a magnesium salt. Done the wet impregnation and then the calcination at 900 degrees C for 12 hours, and what we get is actually this guy. The surface looks a little bit different, but when we actually go into X-ray diffraction, what we see is that both materials are actually retain the same structure, so it's a P2 structure. We have a low amount of impurities in the doped material, and this has to do with the magnesium oxide and nickel oxide. Thanks to the Uter Kaiser group, we were able actually to image with the TEM, and what you can see is, especially if you look, I don't know if the color is can be read so easily at distance, but actually the magnesium distribution within the lamella that we have observed was quite even, although we could see a magnesium-rich and at the same time a nickel-rich spot, and this is pretty much in agreement with the impurity that we have found by X-ray diffraction. Now, what happened actually if we want to make the coating and we want to prevent the doping, we have to follow a different approach. So, of course, what we did was after getting the baseline material, then we we did wet impregnation using a magnesium nitrate source as a source of magnesium, of course, and then we did the calcination at 400 degrees C. We limited the temperature in order to prevent any doping in the bulk. Yeah? So we thought, okay, 400 degrees is not going to be enough to have doping, but we will have the magnesium oxide coating. And well, when we looked at the X-ray diffraction pattern of the two materials, again, both of them, they were phase pure P2 materials, only small impurities of sodium nitrate in the surface-coated material. And then we looked at the TEM and high-resolution TEM with the EDX mapping. So now, if you look at this picture, you basically can see, I hope that you can see, a magnesium layer just on top of the particle. And this is in the range of 20 to 50 nanometers in thickness. Now, we couldn't actually see any magnesium oxide from the X-ray diffraction, from the powder X-ray diffraction data. But doing the selected area X-ray diffraction, then we could actually prove that magnesium oxide is there. Now, we don't have magnesium in the bulk. This is good. So it's pure surface coating. I cannot exclude 100% that there is some doping in the very first few nanometers of the particle. This is difficult to exclude completely. Now we go into electrochemistry. For all the results that I'm going to show, these were basically done at lab scale, let's say. So mainly we're using 3 electrode cells, Zwegelov kind of cells. This is the composition of the electrode. This is the loading, so fairly low loaded, but let's go ahead. The selection of the electrolyte was a little bit more tricky. We were inspired by the work that Sonia did and published in 2019, where actually they proved that the sodium metal can impact directly the performance of your cell, and so therefore what you are actually looking in terms of degradation is more related to the degradation of sodium metal rather than the degradation of your working electrode. So to prevent that, we included a small amount of FEC. Now, if you look, basically, this is only sodium metal stripping and plating. You can see that basically the FEC-free electrolyte, after 600 hours, it just gives up. Yeah? So this is a clear sign of a short circuit. And what we have here, it's much more stable behavior, cycling behavior. We went into electrochemical characterization, as I said, the 3 electrode cells. Now, if we look at the difference between the two materials, so the doped and the undoped, what you can see here, you have a very long plateau, yeah, very flat plateau, and this is also reflected by a very sharp peak in the differential plot. The doped material is different. The plateau is shorter. Of course, we have a little less capacity because we are replacing part of the nickel with magnesium. Now, nickel is redox active, magnesium is not. So some sodium will be trapped just because magnesium cannot change its oxidation state in this case. But anyway, the plateau is shorter, and what we see in the differential plot is that actually the peak is broader, very much less defined. Cycling stability, comparing the two, we see that basically the doped material, the magnesium doped material, has improved performance. It's not perfect, as Max yesterday said. Of course, there is still room for improvement of both particle architecture and eventually also the level of doping. But when we see that, what we can say is that the capacity retention is increased and also the coulombic efficiency. We did, as I mentioned earlier, with Sonia, some operando X-ray diffraction for both materials. So on the left, you see the baseline material, and on the right, the magnesium-doped material. For the P2 pure phase undoped material, we have actually a partial phase transition from P2 to O2. This was new for us. We expected to have a full transition. Probably it has to do with probably the cell capacity didn't reach the value that we were looking for. But then if we actually compare the doped material with the undoped material, we see a completely different behavior. So for the magnesium doped, we have a almost complete phase transition. There is not only one OP4 phase, as it was pretty much announced in literature, yeah, but we have an evolution of phases. And then, thanks to the work of Manuel, Olga, Mosin, and Axel, it was clear that the magnesium doping can actually stabilize the intermediate OP structure. Now, going to the magnesium oxide-coated material. Now, in the upper side, we see the two graphs. Again, a comparison of the uncoated and magnesium oxide-coated material. You see that basically the high-voltage plateau is not affected, so it's a very similar shape of the galvanostatic profile, and this is in agreement with the fact that we don't have magnesium doping in the bulk. Still, we have a better capacity retention in this potential window. Even better if we reduce the potential window to 2.7, 4.3. This would be basically the potential window that you are able to access in a full cell. Yeah? And what we see is that even by switching from 25 degrees C to 40 degrees C, the capacity degradation of the magnesium oxide coated material is actually not affected. As I mentioned at the beginning, for P2 layered oxides, one of the problems is that actually when you have the high voltage plateau, on top of the nickel 3 to 4 plus oxidation, you can have some oxygen evolution. Yeah? So we actually looked at that with the Operando OLEMS. And what we have seen, that at least in the first 3 cycles, for the uncoated material, we have oxygen evolution, and in the first 2 cycles, and CO2 evolution. Now, it seems that the magnesium oxide coating actually shut off any kind of gas evolution. Yeah? So this was nice to see. Of course, we are doing more investigation on that to see whether this is really the case and what are then the the reason behind the still the capacity fade that we see. I also tried to, as in it is in the tradition of ZSW, I also tried to give a projection of the specific energy at the pouch cell when we actually use this material. So as a reference, I think this is pretty standard. Yeah? We get the graphite LFP cell. And then I compared that with the different cell chemistry. Of course, I kept always hard carbon at the anode side. Prussian white, NVP, and then our material, in this case, baseline. What we see that basically is that if we do not pre-lithiate or pre-sodiate, the hard carbon, the capacity or the specific energy will be low. Please note that this is at the stack level. So electrolyte and pouch pack is not included in the weight of the cell. So what we have to do to reach the performance of the specific energy of an LFP graphite cell is actually to pre-sodiate the hard carbon, and I'm glad that there are activities in that respect within Polis. I have to mention also that in this case, I took some data from literature, and the first cycle Coulombic efficiency for the hard carbon, I consider about 75%, whereas for graphite, I consider over 90%. So if we actually can get into the same level, then this gap will reduce remarkably, yeah? And I'm not saying we will be on pair, but probably few percent less. And also, well, this is some homework for us. As I said, our cathodes are in the low loading range, so 4 milligrams square centimeter. Now, if we try to basically build a cell out of it, we will get pretty lousy specific energy. So another thing that we have to think about is how to increase the cathode loading. And of course, this comes with a lot more complication. So we will have to go into electrode development research. This is not the topic of this talk today. And with that, I'm at the end. So the conclusion is that we actually compared the magnesium doping and the magnesium oxide coating on P2 layered oxides. We have seen that basically there is an impact in the performance and improvement of the performance. This is a summarizing graph. Still, the doped material performs better at room temperature and also at 40 degrees C. Now the thing will be whether we have some synergistic effect, so coating plus doping. And this is something in progress. And with that, I thank you for your attention.